During World War II, the German military used a device that scrambled their communications into a seemingly infinite number of gibberish combinations. If you couldn't read the Enigma machine's output, you were fighting blind. The Allied forces gained the upper hand when Alan Turing built a machine designed specifically to decipher that complex mathematics, exposing the enemy's plans. Today, our modern global infrastructure, from the banking system to your private messages and national security files, is protected by classical encryption. These systems rely on a very simple premise. A standard computer would have to guess the correct mathematical key to break in, a process that would require thousands of years of continuous processing to complete. Our entire digital existence is secure only because we assume no one possesses a machine powerful enough to solve those equations faster. That assumption is dissolving. Technology giants are rapidly developing quantum computers, and hardware like Google's Willow chip has proven capable of performing certain tasks at speeds that make classical supercomputers look obsolete. Researchers suggest that an advanced version of this technology could slice through the encryption securing Bitcoin, a process that would tie up standard processors for millennia, in roughly 9 minutes. Standard computers process bits as either 0 or 1, testing password combinations sequentially. Quantum computers use qubits. Through superposition, a qubit exists as 0 and 1 simultaneously, evaluating every mathematical path in a single operation. This processing speed strips away the mathematical walls protecting our private information, leaving our current security protocols completely exposed. The very science that threatens to break global encryption also offers the only mathematically perfect way to secure it. Recently, India achieved a massive technical milestone by successfully establishing a quantum key distribution, or QKD, communications network spanning over 1,000 kilometers. Instead of relying on complex math problems, a QKD network hides the encryption key inside the physical quantum state of actual particles of light traversing a fiber optic cable. This brings the no-cloning theorem into play. In quantum mechanics, it is physically impossible to make a perfect copy of an unknown quantum state. If a bad actor tries to duplicate the particle to steal the key, the clone instantly shatters. While traditional data can be intercepted, copied, and pasted in secret, quantum data is guarded by the strict, inflexible laws of physics. The physicist Brian Greene notes that reality at the quantum level operates on principles that are deeply unsettling and completely defy our everyday intuition. One of those principles is the observer effect. A quantum particle exists in a blurry, multi-state condition until you look at it. The sheer act of observation forces the particle to snap into one definite, measurable state. On a QKD network, this acts as an absolute burglar alarm. If an intruder tries to read the quantum key while it's moving down the wire, their observation breaks the particle's superposition. The collapse immediately alters the error rate of the transmission. It leaves a permanent, undeniable fingerprint on the data, instantly alerting both the sender and the receiver that the line is compromised. You cannot secretly tap a quantum internet connection. The physics of the network will always expose you the millisecond you try to look. Despite the headlines, these machines are not going to replace your home laptop, and they certainly aren't being built to run the latest video games. They are massive, highly fragile industrial systems that require extreme isolation and temperatures plummeting to absolute zero, minus 273 degrees Celsius, to keep their qubits stable. Their real purpose is solving highly specialized computational problems. They will be used to simulate molecular interactions to discover new pharmaceutical drugs, create advanced weather modeling, and accelerate artificial intelligence. We are looking at a specific engineering leap designed to untangle the complexities of the natural world, rather than handle daily consumer tasks. Developing this technology has become a massive geopolitical competition. Superpowers like China and major financial institutions on Wall Street are pouring billions of dollars into building their own quantum infrastructure. Now, India is actively entering this competition. On World Quantum Day in 2026, the country is set to launch its first indigenous quantum computing testbed in Amravati. This initiative is supported by heavyweights like the Tata Institute of Fundamental Research, the Defense Research and Development Organization, and the Indian Institute of Science. For decades, India has primarily been an importer of foreign computing technology. Establishing these testbeds transitions the nation towards designing its own quantum hardware. Developing this indigenous capability means the nation no longer has to rely on imported logic to protect its most sensitive data. These systems represent the practical foundation for a future where India builds the technology it uses to secure its own borders and markets.